I just want to make sure those numbers were okay. So we've got this in solution. This in solution, right? If it's in with water, what this is actually going to do is going to take some protons off of water, right? It's a base. It's not strong, but it's a weak base, but it's a base, and that base will take some protons from water. So let's look at that reaction. This is aqueous. When it does that, it's going to produce hydroxide. So what we have now, we no longer have a situation where we've got an acid in the water. What we've got is its conjugate base, and only its conjugate base. So now what we can do is we can think about this expression. We're not going to worry about the water. We're going to worry about the acetate producing a little bit of acetic acid and a little bit of hydroxide. So we can write this as that. We know this. This is a value that you can look up on a table, or if you give them some other information, maybe you'd have to solve for it, but we can look this up, and it is 5.6 times 10 to the negative 10th. For acetate. That's for acetate. So we know this value. We know this value too, right? This is the 0.6 molar. We have that. So this value, this is going to drop a little bit if it pulls, if it accepts a proton. Right? If this accepts a proton, that concentration is going to go down. However, we're going to ignore that. It should be small, and we're not going to worry about that decrease. We'll worry about that later on. So we're just going to take that to be the 0.6 molar, and we're going to figure out what X is. Once we know what X is, we will know the OH concentration. If we know the OH concentration, well, we could simply get the POH and subtract from 14, and we've got the pH. So we can rearrange this. Well, we do the same thing as we did before. It's Kb, which is 5.6 times 10 to the negative 10th, times 0.6, and then you take the square root. You end up getting 1.83. So I'm just going to get rid of this. That's what we're concerned with. So X, or concentration of OH, equals negative 50. Yeah. And so if we take the negative log of this, POH equals 4.74, so pH equals, let's just round that, 4.7 to 9.3. So down here, I think you just 0.8 equals negative log, well, we just solved it, so equals 9.3. Now, we only have acetate in here. There's no more acetic acid, just acetate. We also have some other things. Don't forget that there are other ions present. They are just spectators. So, right, there was originally HCl. We started off with that. So there's chloride in there. There's sodium in there. And that's it. We said we were adding sodium hydroxide, so that's where the sodium ions come from. They also come from the sodium acetate. Sodium's there, big deal. And we've got chloride, and we've got acetate. So the rest is water. What happens when we add more OH? Right? We put just one more. Let's do another OH unit. Well, now the concentration, again, we're saying this is a magic solution. It stays 1 liter. We added 0.1 moles. It's 1 liter, so that's 0.1 molar. We already saw that 0.1 molar. The pOH is 1. Right? So the pH is 13. So 0.9, pH of 13. I think you can see that. So pH is 13. Now let's graph this. See what we've got. 0 7. Trail off. So, what do we get from this? What's the big deal? And the big deal is, so we can see this the pH difference, right? We did add more sodium hydroxide in this case. So if we added more sodium hydroxide, we would actually end up with a slightly higher pH. But if it's pH 13 or pH 13.7, that's both are quite basic. So what's the importance here? It is this area, right? That area, that plateau shows a very small change in pH compared to this, right? If we look at pH of 4.7, right? That's where we pH equals pKa. It was this, remember the 1.8 times 10 to the negative fifth, pH was 4.7. So if we look around 4.7, if we see 4.7 over here, that's where we are. No, you can't. That's where we are. If we have a pH 7, to get that pH of 4.7 would be pretty difficult because you add just a little bit more acid and you're falling down this hill. You add just a little bit more base and you are climbing that quite quickly. Over here, you get a little bit more acid. Your pH does change. It does go down, and what we're talking about is strong acid and strong base, right? If we add a bit more hydrochloric acid, not talking specific numbers, but add a bit of hydrochloric acid, yeah, we're going to go this way on the curve. Notice the pH is not changing a whole lot, right? We're going from 4.7 to 4.6, 5, 4. Here, we go from 4.7 down to 1 up, or 1.2, pretty quick. And if you've got a reaction, or if you've got some experiment that you're doing where you need a reaction to proceed at a particular pH, then that's when you want to use a situation like this, where you have a weak acid and a conjugate base present, and they are going to prevent this wide swing in pH that would otherwise exist. So that's day one. So good luck.